That was like 4. Okay, so one of the big things, guys, in physics is measurement. Okay? We need to recognize that some things are measured differently than others. Okay? So as a result, we have two kinds of quantities in physics. We have vector quantities and we have scalar quantities. Okay? A scalar quantity is described differently than a vector quantity is. Okay? So as an example, if I was to tell you the distance from Okotoks to Calgary, I would tell you that that is about 35 kilometers. If I was to tell you the displacement, which is a vector quantity, I would tell you that Calgary is about 33.2 kilometers at 13 degrees west of north. What's the difference? What's that? I'm a bit more specific, yes. Okay, but what did I put on the vector description that I didn't on the scalar? Yeah, I gave you degrees. I told you which direction to go. Yeah. Okay. So in a vector quantity, we have the measured value, and then we have a direction. A scalar quantity only gives us the measured value. Okay. Now, some things, okay, are going to be definitely scalar. Like, for example, my mass. Okay. My mass, I'm not going to tell you what it is, okay, is a scalar quantity because it doesn't have direction. It's just how much of me there is. Okay. If I eat more, there'll be more of me, and I'll have more mass, but it doesn't change which direction it is. It doesn't have direction. It's just me. Okay. Same with time. Time is scalar. Okay. It's 3 hours, or it's 5 hours, or it's 20 minutes, or whatever. Okay. We don't say 20 minutes right, or 5 hours left. Okay. Time doesn't have a direction. Time only goes forwards. Unless you have something I don't. If you have a time machine at home, we should talk. It's just things I would change in my life. Okay. All right. Now, the other thing we have to realize about measurement and scalar and vector quantities and things like that in physics is that as North Americans, we have a completely screwed up way of describing distances to people. Like, it's horrible. We are terrible at it. Okay? Canadians, Americans, we're awful at it. Okay? Let me demonstrate. Wow. How far is it to Edmonton?
300 kilometers.
Okay, that's good. You know how many times I actually get the right answer? Not a lot. Not a lot. How many of you were thinking 3 hours? Because that's how we think. Okay? I asked about how far is it to Edmonton, and automatically our minds go to how long will it take me to get there. Here's the problem with that. That's variable. It's not always 3 hours to Edmonton. It depends on how fast you drive. Okay? If you go the speed limit, yeah, it's a little under 3 hours to get to Edmonton, provided you don't stop anywhere. Okay? But if it's winter time and the roads are bad, it can be 8 or 9 hours. But here's the thing that doesn't change. Edmonton's always the same distance away. Okay? If I take Highway 2 to Edmonton, it is never further. It's always the same distance. Edmonton and Okotoks are a certain distance from each other. Right? That does not depend on anything else unless the continent cracks right open down the middle. Okay? Then it might be farther away. That's not going to happen. Okay? Everybody follow me on that? Okay? But so we have to change our thinking a little bit because that can really get us in trouble when we start talking about, how a question might ask, how far is it from this place to that place? If you write in a time, you're wrong. Okay? No, you don't. You get out of the way. All right. So it's very intrinsic, our motivation. No extrinsic reward system. Okay? All right. So we need to understand that there's lots of different ways of measuring how far apart or how fast objects are going. We need to differentiate between distance, displacement, speed, and velocity, because probably up until today you thought speed and velocity were the same thing. Okay? They measure the same thing, but they measure it from different points of view. One of them is scalar, and one of them is vector. Okay? Speed is scalar. That's why the thing in your car is called the speedometer. It tells you your speed. It does not tell you your velocity, because if it did that, it would have to take into account what direction you're going. Okay? Similarly, if you ever get pulled over by the police, their first question to you is usually, how fast were you going? Okay? Do not tell them, I was going 130 kilometers per hour at 10 degrees west of north. Because you'll give them your velocity, and they will have a follow-up question. Have you had anything to drink today? Okay? That's just good bad. Okay? You don't want that. They ask you how fast you were going, they want to know your speed. I was going 130, sorry. Okay? No, you don't lie. They know how fast you were going. They pulled you over because of how fast you were going. Don't lie to them. They're making conversation. They're trying to see whether they're going to write you more tickets or less tickets. Just be honest. I was speeding, officer. I'm sorry. Okay? I also have no weapons in the car, and I am not a threat to you. Okay? No, really? I don't.
If you say that, they're probably more suspicious. I'm not smuggling.
Well, you can put them, there are ways to put police officers at ease, and one of them is to say, you can see my hands, I'm not going fast, okay? Like I had this happen with a stranger. Honestly, like I had this happen when I was coming from a fishing trip the other day, fishing wildlife, and I was just doing a check on everybody. No, and he asked, they were pulling everybody with checking licenses and stuff, and he wanted to see my license, which was in the back seat. Oh, right? It wasn't on me. So I said, okay, it's in the back seat. I'm going to get out. And so I got out and I said, by the way, I have, if you want, I can open the door, but I have no weapons. Because lots of people were hunting at that time. You could have a rifle in the back. That's scary if you're the officer. So I just said, I have no weapons. It's always a good idea. Okay? So what do you mean? We're digressing a lot. Okay? But, so, differentiating between those, we have to understand which ones are vector, which are scalar, and then we're going to solve problems related to that. So, there's going to be quite a bit more math and algebra in this unit than there has been in any other. Okay, that's fine. Algebra is easy. You guys are going to be fine with that. Okay. I will be giving you a formula sheet. Okay, and you do need a scientific calculator. You're going to need it every day for the rest of the unit. All right. You can use your phone as long as we're not doing an exam, okay, like even on a quiz, I'll let you use your phone because they're not worth very much, but okay, you do need to have a scientific calculator. It doesn't need to be the really expensive graphing ones yet. You need those for math, you don't need it for this. Okay, the $8 like Wally World job would be. Okay. All right, now a couple of other things about physics. We need to understand the metric system in physics. And I've discovered that you guys don't. Okay? Yeah. So it's not good. So I did put it in the notes package. Yes, I did.
Why is this one package different than the other one?
Because it's a
They were not so style, but this one is like second style. The other one was not style.
Oh no, it's just the first couple of lessons, then it goes back to my notes.
Oh, okay. So I like
But is it in the physics room?
We're not using yards over there.
No, we're not. Where's it in the worksheet? Anyway, I'm going to pull it up for Okay, so we're going to look at this, guys, because we got to go over the metric system here, and we need to go over it in a big way. Okay, so here's the beauty of the metric system. The metric system operates on a base of 10, just like our numbering system does. Okay, that makes it work a lot better than the imperial system, because you never have to memorize dumb things like there are 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile, 3 miles in a furlong, whatever. There's all kinds of, there's 2 point, what is there, 16 ounces, 8 ounces in a pound. I see, like, I can't even remember it all. Okay? In the imperial system, you had to remember all of these weird numbers. None of them went together. Okay? There was no real rhyme or reason for why there was this one was at 8 and this one was 12. Okay? It just was hard to remember. In the metric system, anytime you make a leap from one level to the next, it's 10. All right? So if I'm looking at the metric system, it's set up with base units. Okay? Those base units measure certain things, like meters measure distance, grams measure mass, liters measure volume. Right? But this can be applied to basically anything. We even apply it to memory on computers. Okay? The base unit of memory on computers is a byte. Right? If you have a decabyte, that's 10 bytes. A hectabyte is 100 bytes. A kilobyte is 1,000 bytes. We don't even measure anything in those anymore. Okay, because everything's way bigger than that. Then you got a megabyte. You see that sometimes. Okay, a gigabyte, right, and so on, all the way up to terabytes. Right, we got terabyte hard drives. That's 1,000 gigabytes. Okay, now, so what we have to learn here, guys, are how these prefixes work. Okay, every time you move from one prefix to the next, you're moving down a base of 10, at least through the first 6. Okay? Then after that, it goes down by factors of 1,000. Right? So if I have, okay, let's say I have 100 meters. If I have 100 meters, okay, so let's just do this as an example. If I have 100 meters, how many centimeters do I have? Okay, so here's where meters are. Okay, here's where meters are. Okay, if I have 100 of those, I have, okay, centimeters is like 2 more down from that. Agreed? Okay, do I have more centimeters than I have meters? Yes. Okay, so here's how many meters I have. Here's where the decimal is. How many spots down from meters is centimeters? Okay. All you're doing when you're converting through the metric system, because it's a base of 10, is moving the decimal. All right? So, if I have 1,000 meters, how many kilometers do I have? 1. Okay? Kilo is how many spots above it? 3. And everything's a base of 10 in our system. So if I have 1,000 meters, here's where the decimal is. There are 1,000 meters in a kilometer. So that's 1, 2, 3 spots, 1.0 kilometers.
Just common knowledge.
I thought it was. It was to me, because when I was a kid, that's when this happened, when we converted over. They made us memorize all of this. Okay? We had to memorize that there are 10 decameters in a meter. Okay? Sorry, 10 meters in a decameter, so backwards. Okay? 100 meters in a hectometer, 1,000 meters in a kilometer. We had to memorize all that. Okay? What you guys should do is you should memorize these 6. Okay? You really should. Okay? Beyond that, I don't expect you to memorize it, but I expect that you understand that each one of these shifts is a factor of 1,000. Okay? So you can see here, if I have 1 meter, okay, moving up, this is a decameter is 10 meters. A hectometer is 100 meters. A kilometer is 1,000 meters. Okay? A megameter is 1,000,000 meters. Okay? A gigameter is 1 billion. Okay? Everybody with me there?
What's the biggest?
Exa. 10 to the 18 meters.
What is that like? Biggest?
That's as far as I know. No.
So maybe.
Okay, and then if you go further down, okay, we used micro back in the biology unit. We used micro to tell us how big things were, right? When we were looking at it through the microscope. 1 micrometer is 1,000th of a meter. Okay, sorry, not 1,000. Sorry, it is 100,000th of a meter.
What would the Avogadro structure be for?
I don't know what the prefix.
It's to the 23.
It's to the 23. There probably isn't any.
Or not a prefix.
Yeah. Okay, so here's what we need to remember. In the metric system, anytime we convert, okay, and I've got these actually pasted up here. I will put a copy in Google Classroom of this so that you can have it, okay? But anytime we're making a conversion in the metric system, okay, we're moving the decimal a certain number of places. Most of the time, okay, our conversions take place between these 6. Okay, we very rarely go lower than micro. We very rarely go higher than kilo. Okay, so if it's something in kilometers, thousands of meters. Okay, you're all right with that? Yeah. So we'll probably look at that a little bit more, but I wanted to just kind of introduce that right now so that you guys understand how the metric system works. Okay, so the ones we'll be dealing with most often will be deci, centi, and milli, and we don't deal with those a whole lot in physics. We deal mostly with going from meters to kilometers. Okay, that's our most common one. There's 1,000 meters in a kilometer. It's really something you should memorize. Okay, now scalars and vectors. If you've ever gone hiking off trail, this kind of illustrates what we were doing just a minute ago. The way we typically describe distance is worse than useless. Okay, and I will give you an example of that. A buddy and I were hiking in Kootenai National Park, backpacking actually. We're on a 3-day backpack. And it was on our second day. We'd gone over 2 passes. We'd already hiked like 28 kilometers, and it was, getting close to like dinner, and we were tired and hungry, and we still weren't where we were supposed to be. And we were starting to get a little concerned because we really thought we should be already. So anyway, we're kind of just sitting down and taking a little break and collecting our thoughts. We see this guy come like nearly running towards us, and he's got like a way bigger pack than us. Like he had to weigh 100 pounds easily. Okay, and he was like wearing like army fatigues and stuff. We didn't think about it at the time. This is all after. Okay, he comes running up towards us and like, "Hey, how's it going?" It's like, "Oh, good, good." Barely out of breath, running uphill, carrying 100 pounds on the back. We're like, "Hey, did you come from Tumbling Creek Campground?" "Oh yeah, it's like 20 minutes that way down the trail. 20 minutes." We're like, "Oh, sweet." We're so hungry and tired. Okay. And he was funny. He was like a Navy SEAL on vacation, probably in way better shape than 2 teachers on summer vacation. So we're like, "Sweet," put on our packs and started trudging down the trail. An hour later, like we're cursing this guy. Like if he wasn't so fast, we were going to hunt him down. We were mad. There's no hope we'd have ever caught him. We'd have to run back uphill. So anyway, we finally an hour later get to the campground. Like, holy! And then both of us being physics guys went, "Oh yeah, right." Once we got some food in us, we're like, "Not straight anymore." It's like, yeah, he was running. He was in really good shape, and that's why it only took him 20 minutes to cover the distance it took us. That's all. Okay. So yeah, when we talk about distance, you should never tell somebody how long it took, because that's worse than useless. Okay, you got to say it's 3 kilometers down the trail. By the way, is that a scalar or a vector quantity? I said down the trail. I gave direction, right? Now the trail probably changes direction, but it's kind of vector because I did say which way to go. Okay. But 3 kilometers, okay, is a much more accurate. We would have known, okay, it's going to take us about an hour, because we knew we averaged about 3.5 kilometers an hour most of the time.
So you were saying you're going back in time, is that a vector too?
Well, I said that you can't do that. But yes, technically, if you were going backwards in time, you would have to say this many years in the past. That would put a direction on it. Okay. But for us, we only perceive time as going forward.
So is it even if it's a vector, even if it's not like the most specific, like down the trail? It's like,
yeah, down the trail. I mean,
like,
that's not a
the trail,
great vector.
Yeah.
Most of the time, we give a specific vector. This many degrees, like a compass direction, or right or left or up or down.
Without the direction.
As long as it's a straight line from where you are, yeah. Okay, so if you ever gone hiking or off trail or anything like that, okay, this is what we know. Now, most of the time, you have signage on a road or a trail, okay? Now, is that signage telling you a vector quantity or a scalar quantity most of the time? Okay, it's just one of the ones that says distance on it. That's just scalar, right? Like it says, Calgary, 35 kilometers. It doesn't say, it's not like an exit one that says Calgary, exit to the right. Okay, it's just Calgary to Spar, or Edmonton to Spar. Okay, and that makes sense. In a situation like this, if I'm right here at Seldom Inn Campground, okay, because that's what this one is called, okay, if I'm here at Seldom Inn Campground, just outside of there is a sign that says 27 kilometers to Snake Indian Falls Campground. Okay, now that 27 kilometers assumes I'm going to do what? Follow the trail. Okay? It wouldn't tell me it's 27 kilometers if it expected me to do this. Because then it would have to say it's, well, obviously less than 27 kilometers, probably more like 19 kilometers, and it would have to tell me it is 35 degrees north of west. Okay? And it could do that, but I wouldn't want to go this way. Okay? Because there's, well, rivers, which usually have deep canyons, glaciers, big tall mountains to climb over. It's not a three-dimensional map. Okay? So yeah, I wouldn't go that way. It makes more sense to give me a scalar description of how to get to Snake Indian Falls Campground than it does to give me a vector description. If I'm a helicopter pilot, then sure, okay? I would want that vector description. That's not a good situation. If I'm following a path or following a road, I want a scalar description. I'm already on the path that's going to take me there, and that path is going to change directions. So you can't really give me a vector description. Okay? If I'm flying, then yes, I do need a vector description because I can go in a straight line. Okay, so like we were saying here, okay, we say Calgary's 40 kilometers away. We make no reference to which direction Calgary is. We just get on the road and follow it. Okay, in that case, we've made a scalar description of where Calgary is, and we've given the distance because distance is scalar. Okay, if I say that Calgary is 40 kilometers, 13 degrees east of north, then I've given you a vector. Okay, which one's more accurate? Okay, I said 40 kilometers east of north. I said 40 kilometers. Accuracy doesn't come from amount of detail. It comes from measurement. These two numbers are measured to the same level of accuracy. They are accurate to plus or minus 1 kilometer. This number is more accurate than those numbers because it's measured to the nearest tenth of a kilometer. So it's accurate to plus or minus 100 meters, where this one's accurate to plus or minus 1,000 meters. This number, even though it's scalar because it has no direction, is more accurate than these numbers. Okay? But we get that impression, right? We see that extra information and automatically we say that one's more accurate. Accuracy comes from measurement. Okay? I haven't measured that 40 kilometers any more accurately in the vector description than I did in the scalar description. Everyone follow me there on the difference between accuracy and detail? All right, so let's look at, I had a better version of that. I don't, okay. We have to use my hand-drawn ugliness here. I don't want to erase up there. Okay, so let's say I want to go from my house, that's what that is, to Walmart. Okay. Now, obviously, I can't walk straight from my house to Walmart because I don't live right beside Walmart. Okay, so I would have to, follow sidewalks and walking paths and things like that. Take the bridge across the river. Okay, and then walk the rest of the way to Walmart. So when I walk there, when I get there, let's say that means I have actually walked 4 kilometers. Okay? Is that the distance I've traveled, or is that the displacement from the house? It's the distance. Okay? This is a scalar quantity. I gave no direction because I can't. I went lots of different directions on my way to Walmart. All right? Now, if I had a helicopter, I wouldn't shop at Walmart. I'd shop at way nicer places because I'd have a helicopter. Okay? But let's say I had a helicopter and I was flying to Walmart. Okay? I can fly to Walmart in a straight line. There's no obstacles. Okay? To me, I can just go in a straight line. Is that going to be shorter? Yes. Yes. Okay. So that short line there, okay, could be, let's say, and we'll say 30 degrees south of east. Okay, so it's short. Is that a vector or a scalar description? Vector. Okay, so this is the thing we need to understand. I don't know why it was there. Okay, so this here is distance. This is displacement. Okay, so distance is represented with a D. Okay, displacement is a D with an arrow over top, denoting that it has direction as well as magnitude, and that it is a vector quantity. Okay? So distance tells me how far it is from one place to another. Displacement tells me how far I've gone and in what direction. Okay? How far have I displaced myself in a straight line from my starting position? Okay? So displacement talks about my change in position, whereas distance tells me how far did I go in doing that. Because usually I go farther because I can't have traveled in a straight line. All right, we're going to leave it at that, and we'll talk more about that tomorrow. Okay? Have a good day.